Uh, Firstly, let's introduce our background and problem statement. The objective of car rental company is to maximize its profits by determining the optimal numbers of cars to own and their distribution across 4 depots, that is, Glasgow, Manchester, Birmingham, and Plymouth, over the course of a week. The company faces varying demand for car rentals at each depot from Monday to Saturday. Rental durations can be from 1 to 3 days, and cars can be either returned to the original location or transferred to a different depot. And then when we come to our key data, first, the daily demand table shows the number of rentals we need at each depot from Monday to Saturday. Next, our rental prices are determined by the rental duration and returning depot. We also have transfer costs for moving cars between places, and we must consider our marginal cost per rental, which covers wear and tear and administration. A critical factor is repair cost, that is 10% of return cars are damaged, and incurring a 100 fee each. And finally, note that only 2 of our depots, as indicated in the repair capacity table. This data is essential for our following planning.
And the left table shows the daily expected rental demand for each depot from Monday to Saturday. For example, we can see that Glasgow has a demand of 100 cars on Monday. What we should be attended is that we don't need to meet all the demands. Also, a key detail here, Sunday is closing day. It's not included in rental days, so rental periods essentially skip the Sunday. Our goal is to balance costs and profits. The right table outlines the return proportion of cars rented from each depot. Taking cars rented from Glasgow as an example too. 60% are returned to Glasgow itself, 20% to Manchester, 10% to Birmingham, and 10% to Plymouth. For car transfer table, it shows transferring cars between depots costs money and takes time. 10% of cars returned by customer are damaged. When this happens, the customer is charged an extra $100. The car has to be transferred to a repair depot, where it will be repaired the following day. The cost of transferring a demand car is the same as the undamaged one. We can see orange region. Only 2 of the depots have repaired capacity. The capacity at each repair depot is on the right-hand side. After being repaired, the car is available for rental at the depot the next day or may be transferred to another depot. Revenue is affected by rental cost. The profit calculations must consider the operation cost, transfer cost, and the profit of rentals. The rental period is independent of the origin and destination. 55% of cars are hired for 1 day, 20% for 2 days, and 25% for 3 days. The opportunity cost per week is $15.
Okay, the next is the network representations. It's about the load and the art. The load is about the depot and the repairs depot. The depot is represented as nodes where cars can be rented or returned. It's about Glasgow, Manchester, Birmingham, Plymouth. We can see it's the GMBP. The repaired depots include within above the nodes M and the B, where damaged cars can send for repairs. The arts represents the possibilities of retaining a car at a depot, returning it the same or another depot, or transforming cars between depots. Cars between depots are direct. For example, cars moving G to M with special cost associated with each transfer. We can see the next. The next is we can see the figures show the nodes and the arts and the function. The function is about the objectives to maximum weekly profit, considering rentals incomes minus cost. The perimeter depends is about the demand and the transforms cost, a rentals cost, original rentals cost, repaired capacities, owing costs, and damaged card fees. The next is about the design variables. It includes the total cars owned, the cars available, cars rented, cars transformed, damaged cars, cars under repaired. The next is about the constrictions. The constriction is about the four levels. One is ensures cars rented no more than demand for all depots and days. Equals available undamaged and damaged cars at the beginning of the days based on rentals and repairs. Next is ensures total cars sent for repair don't exceed each depot's repaired capacity. This means cars under repaired no more than repair capacity. Next is total number of cars owned is equal to the number of rented out and accountant for damaged or returned cars.
In this section, we used how to solve our MCNF model for the car rental system. Our goal was to find the optimal number of cars and their daily allocations across cities that maximize the company's total profit. Okay, next page. With all decision variables and constraints to ensure the inventory is balanced, every day the number of cars coming in must equal to the number of cars going out, and plus the number rented to customers. Finally, we set our objective function to maximize the total revenue minus total costs, including ownership, transfer, and repair costs. And going to next page, we solving the problem with pulp. The solver status return optimal, which means we successfully found the best possible solution under all given constraints. And the results show that the optimal number of cars to be owned is 670, and the maximum profit is about it's over 121,000. So we can do some interpretation. We can interpret the results now. Here we can see the optimal daily distribution of cars. For example, in Birmingham, around 146 undamaged cars are available on Monday, and about 86 are rented out. These are perfect situations. Yes, and next page, from the sensitivity and analysis, we can see that our model is most sensitive to price and repair capacities. Relaxing these constraints or improving repair capacity can significantly boost our profits, while other parameters such as transfer or ownership cost have relatively minor effects. That's all for the pulp section. Next section will be network X.
We also solved the problem in network X with a time expanded graph. Note tracks states over time UDT for undamaged cars, DDT for damaged, and gate nodes handle return or rent. Edges encode business rules with capacities and costs. Holding inventory, renting, revenue as negative costs. Returns after 1 to 3 days split by damage probability. Repairs through Manchester and Birmingham transfers. Rounding network simplex G gives the continuous minimum cost, which maximizes the profit flow. Because flows can be fractional, we apply a largest remainder rounding to rental counts and recompute downstream stocks to keep feasibility with negligible objective loss. The tables summarize the optional plan. Undamaged inventory begins the week high at Manchester and rebuilds towards Saturday as return arrive, especially at Birmingham and Glasgow. Rented out volumes mirror demand patterns. Monday is strongest for Manchester and Plymouth. Midweek moderates and critically, Saturday rentals remain positive across all depots. Resolving the all-zero Saturday issue is seen in early attempts. Damaged inventories peak midweek and decline as repairs clear through the two repair depots. Overall, this approach yields an auditable model, fast solve, and an integer plan that is operationally ready with minimal loss in profit. And why we get different results by these two methods. Let's go to the next part.
Okay, let's walk through the final part, results analysis. We'll start with the model comparison. PULP returns a maximum profit of about $121,000. By comparison, the Network X model comes in higher at about $138,000. In short, Network X achieves the higher profit on our instance. In terms of the number of cars, ULP recommends owning 617 cars and allows 617 maximum daily rentals, while Network X recommends 605 cars with 605 daily rentals. So both models point to an optimal fleet right around 600 vehicles. On running time, both are fast. PULPA is slightly faster because Network X is more complex. Now, we discuss sensitivity. We vary different variables and observe how the solution responds. Thirdly, high price sensitivity. Both models are highly sensitive to price changes. A small price change moves the objective materially. Secondly, the optimal number of vehicles stays close to 600 in most scenarios. Finally, in every scenario, Network X produces a higher absolute profit than PULP.
Okay, now I will introduce the PULP model, the advantages. The first one is modeling flexibility. It's straightforward to add non-business rules. For example, weekends, rental caps, repair bay limits, or inter-depot transfer restrictions. Second one is comprehensive verification. We get full optimality certificates and can audit primal feasibility and reduce the costs, which is useful for governance. Then it's reduction analysis. We can systematically relax constraints to quantify their value. For instance, what's the profit gain if we loosen repair capacity? Then is interpretability. Each constraint is explicit and maps cleanly to policy, which helps explain results to non-technical stakeholders. Then is the advantages of Network X model. It also brings clearly strengths, higher profit in our experiments, thanks to a lean formulation tightly aligned with mean cost flow. Then is integer solution guarantee with integral supplies, demands, and capacities. Mean cost flow returns integral flows for any final reporting that needs whole vehicle by day and depot. We apply a simple largest remainder tie break, though in most cases integrality already holds. Then is realism. It's a naturally capture initial inventory and time expanded flows, staying close to actual operation. Computational efficiency. Network flow are optimized for this structure and scale well with graph size. Then it's a summary and a recommendation to include both tools work, but they trade off different properties. PULP favors precision, auditability, and rapid, which if analyzed, while network favors link speed and a slightly higher profit in our tests. The core business targets to balance ownership, transfer, and repair cost against rental revenue to maximize weekly profit. The results consistently indicate an optimal fleet around 600 cars, with profit primarily driven by pricing. Recommended next steps is stress test price bands and transfer costs and choose the implementation based on needs. PULP for policy heavy scanners and explainability. Networks for producing deployment where speed and integer flows are paramount. Okay, thank you.